Hello students, welcome to my classroom chemistry classes. So we are discussing the topics like advanced JEE advanced topics. So for today's session, we have the topic chemical equilibrium and ionic equilibrium, and we will be seeing this as totally as an equilibrium. So like what we discussed in the previous topic, the same way today also we will be seeing this topic or revising this topic through these concepts of this equilibrium through like some applications, theoretical kind of numerical applications. We will revise this topic. So hope you will utilize it again, and let us start with some basic applications and we will revise it. So when we just say an equilibrium, when we reach actually an equilibrium, we generally say the reaction where the reversibility is there, then such reactions where the rate of forward reaction and backward reactions becomes equal. That is what we have already represented in the diagram there already. So at that stage, the equilibrium will be attained in the reversible reactions. But even we can say as the conceptually, like the problem now what we have here, so the equilibrium is even attained when the Gibbs free energy change for the reaction becomes equal to 0. That is, the delta G becomes equal to 0. So that this concept, this numerical application is based on that only. That is, at 27 degrees centigrade, the rate of forward reaction is at a time t is e to the power of 4 times greater than the rate of backward reaction. But we just use when an equilibrium is reached, at that condition, the active masses of the reactant and products becomes a constant. So that active masses we may be expressing in terms of concentrations, we may be expressing in terms of mole fraction or partial pressures. So we have different equilibrium constants. That is, the equilibrium constant for the reaction is generally expressed as, suppose if you take an equilibrium reaction, K equilibrium will be always given as the active masses of product. That is, well, let us say we are writing as concentration here. So it is active masses of products to active masses of reactants. But at this stage where we just used as rate of forward reaction is equal to rate of backward reaction. So when we write the rate constants expression, we say K equilibrium is also nothing but Kf by Kb. That is, rate of forward reaction to backward reaction ratio can also be taken as an equilibrium constant. So what we just use now, rate of forward reaction is also again when the concentrations are fixed, then it is directly proportional to Kf or rate constants. So we just say this is also nothing but rate of forward reaction to the rate of backward reaction. So what he said is the rate of forward reaction is e to the power of 4 times, means K equilibrium value is nothing but now e to the power of 4. But from the thermodynamic relation, we can say the delta G naught is equal to, since delta G is 0 for the equilibriums, so delta G naught is given as, or we can take it as minus RT ln K equilibrium. So this is now what we wanted to have, what we have to calculate the change in magnitude of free energy change involved in this. So we want only just a magnitude. So we don't use this negative sign there maybe. So for our let us say, means this concepts are suppose asked, this type of application is asked, or question is asked in, let us say, numerical, then it cannot be, sign will not take. So we take the magnitude value, so that it is minus. Now we have to calculate in calorie, so that we can take this R value as 2. Then temperature is given as 27 degrees centigrade. So we can take the temperature as 300. Then ln, it is e to the power of 4. So it's nothing but 4. So it is minus 2 into 300 into 4, because ln E is 1. Everybody knows that. So it is nothing but now 6 into this 2400 calories. Clear? So we need only the magnitude. So we can take this 2400 as our answer. Anything clear for everyone? So the delta G is 0. So we will just say delta G is equal to, suppose, delta G naught. How we got this expression is plus RT ln K. Is it clear? So that we use that expression and we said delta G is 0 at equilibrium, and we have taken this expression and derived this. Okay? Then now at some temperature, now this question is at some temperature under a pressure of 4 atmosphere, PCl5 is 10% dissociated, and calculate the pressure at which it is 20% dissociated. So it is like this type of applications whenever it is coming. Mostly it comes with a gaseous reactions, and where the reactant generally taken as unity or 1. So that when we take the here PCl5, which is a gas, is dissociating into PCl3 gas, Cl2 gas. So that what we use like a degree of dissociation whenever anything is asked. So let us say he asked at a particular temperature pressure what is the degree of dissociation is given, and he gave the degree of dissociation might be 20% or some other value at a different temperature. So what we try to do in such cases is we try to derive an expression in terms of degree of dissociation with a pressure relation. So where we can do that, where the Kp expression, when the active masses of the reactant you are expressing in terms of partial pressures. So that for a degree of dissociation derivation, because degree of dissociation is nothing but number of moles that are reacting for every 1 mole. So what we do is, in such cases, whenever it is not given, whenever the quantity of the substances are not mentioned, so what we do is always we consider it as 1 mole. So let us consider it as 1 mole and let us derive an expression for the alpha and P relation for the Kp. And what we do with that is, since Kp remains same, or equilibrium constant of any reaction remains constant, as we don't change the temperature, always any type of equilibrium constants remain constant. So even we are going to a different pressure, degree of dissociation might change, but K value remains same. So we use that expression, means that condition, and from that expression we can use that alpha and P relation and can derive or can calculate at what pressure now the degree of dissociation might be here 20%. So let us see. So take it initially 1. So you can even try this way. P is equal to 0. Initially we have taken 0. So this is 1. And PCl3 and Cl2 will be 0. And generally we say the degree of dissociation in terms of alpha. So if alpha is the degree of dissociation, then that alpha is reacting here. So when we reach an equilibrium, that is time of equilibrium is attained, how much of PCl3 might be left in? 1 minus alpha. So that when the proper reaction is taken, the stoichiometry we use it. So what we say, if 1 mole of PCl5 is reacting, we will get 1 mole of PCl3 and 1 mole of Cl2. So if alpha moles of this is reacting, then we get alpha moles of this and alpha moles of this. But what is partial pressure, sir? The pressure exerted by the individual gases in a mixture of gases. So when we just know the number of moles of each component, the partial pressures can be determined using the Dalton's law of partial pressures. So what Dalton law of partial pressure says and how we derive from there? Partial pressure is nothing but mole fraction into total pressure. So total pressures are mentioned here. Total pressure is, we have to calculate the other one. So let us say total pressure in terms of, let us say, like as a P variable. So what is partial pressure is? We can say partial pressure as mole fraction into total pressure, P total. So what is the total number of moles? So total number of moles here at equilibrium is 1 minus alpha plus alpha plus alpha. So it can be, let us say, we take plus or 1 plus alpha. So that what is partial pressure of PCl3? It will be number of moles of PCl3 by total moles, that is the mole fraction, into P total. So we, let us say, if I write a PCl3, which is also equal to PCl2, in this case, because number of moles of PCl3 and Cl2 what we are getting, it's only from the PCl5, you will get in unequal quantities because their ratios are also 1:1. So what is this now? Is nothing but alpha by 1 plus alpha into P. So what is P? PCl5 will be. It's nothing but 1 minus alpha by 1 plus alpha into P. So if you use this type of expression, directly we can able to measure. So let us say in a derivation form. So what is Kp? It's a P PCl5. That's 1 minus alpha by 1 plus alpha into P by alpha by 1 plus alpha into P, that is PCl3 into Cl2, that is, sorry, this is reverse, no? So we have to write PP. So this is what we have to write, like alpha by 1 plus alpha into P. This is PCl3 as well as Cl2. So square we will write directly. Then 1 minus alpha by 1 plus alpha into P. So what is its expression will be? It's alpha square. This P, one of the P gets cancelled, one P left, and in the denominator also 1 plus alpha gets cancelled and 1 plus alpha completely goes in this denominator, but 1 plus alpha remains in the numerator, so that it is 1 plus alpha into 1 minus alpha. So it's overall as 1 minus alpha square into P. Clear? So what we use now, we can take the Kp remains same, so we can take like this now. So what is this we use? So that now Kp same at different pressures, different alpha values may exist. So it is 10%, that is 0.1 whole square at a pressure of 4, what is given? This is nothing but 1 minus 0.1 whole square is equal to, what we need to calculate, where the degree of dissociation is 20%. So it is nothing but 0.2 whole square by 1 minus 0.2 whole square into P. That is what we can derive from simplifying this. Clear? So what we get, you can just see. So it's 0.1, that you can cancel it, it will be 4. Clear? So this is 4, this 4 gets cancelled. So this is nothing but P. This part comes to the numerator, that is, what is this value? 0.04. So 1 minus 0.04, nothing but 0.96. So we are cancelling this directly, so that it is 0.04, 0.96. This is 0.01. So partial pressure of that is nothing but 96 by, because it comes to numerator. So it is 0.96 by, this is 0.01. So it is 99. So this is the pressure in terms of atmosphere, because we are taking the P value in terms of atmosphere. Clear? So this is 96 by 99 atmospheres. Okay. So derive the expression for the Kp or equilibrium constants, and because it remains same, so we can use that and determine the degree of pressure at a different pressures or alpha at different pressures, that we can do. So this is the simplified expression. Also, if you can remember, it is suppose like PCl5 type equilibrium, alpha square by 1 minus alpha square into P total. Okay, that helps us instead of deriving. Then let us see next. the vapor density of the mixer. So this is also in a similar concepts. The vapor density of the mixer is given. So we have even a similar expression now. It is derived when a gaseous reaction is there. Vapor density of the mixer, equilibrium mixer with the initial vapor densities, we can compare and we can derive an expression. What is that expression for the degree of dissociations is? Same like PCl5, which is in equilibrium with, suppose, with PCl3 plus Cl2. Same way, if you use this is a 1, this is 0, this is 0, this is 1 minus alpha, this is alpha and alpha. So total moles at equilibrium is again same like this also. What you get is 1 plus alpha. But what we say with relation to this is moles. Moles are always proportional to 1 by molecular mass. Because weight is always conserved in any reaction. That is when the gaseous components or any components are not going, and even if a reaction is, let us say a gaseous component is involved in the equilibriums, we have to do such reactions always in a closed conditions. Otherwise, there won't be any reversibility if the component is living. So we have to do always such reactions in terms of or in closed vessels only. So when closed vessels are there, mass is not lost, there is no loss of mass, so that weight is conserved. So we say moles is inversely proportional to molecular mass, but molecular mass and vapor densities are directly proportional. So you say it is also inversely proportional to vapor densities. So initial moles are proportional to vapor density, 1 by vapor density, like that. So that what is initial moles we have taken 1. What is equilibrium moles? 1 minus alpha, 1 plus alpha. So what you see is, suppose if I take the equilibrium moles here, that is 1 plus alpha by initial moles as 1, we get now as the ratio of moles at equilibrium to this we have taken. So it is initial to this. So initial we generally write as capital D and equilibrium vapor density as small d. Clear? So what is this alpha now? So alpha is simply now D minus D by small d. But we know initial vapor density, because initially we have started with only PCl5. So what is vapor density of PCl5? It's molecular mass of PCl5 by 2, because initially 1 mole is there. So what is this now? It's molecular weight of PCl5, that is PCl5 will be, phosphorus is 31. So it is 35.5 for the atomic mass of chlorine into 3 times. So 5, 16, then 106, 15, 10. So it is nothing but 106.5. So it comes as 5, 7, 3, 1 like this. No, 5, no, 5, PCl 5. So it's 5 times, sorry, 5 times you have to multiply. So 5 to 7 to 15, 17. So it is 177.5, nothing but 5802. This is by 2, will give vapor density, that is capital D. So that is 104.25 is the capital D value. Clear? So what is this now? 104.25 minus the equilibrium vapor density is given as 92 by the again equilibrium vapor density, that is 92. So it's only just again solving it. Clear? So whenever we have a reaction with initial reactant moles as 1 and we have some gaseous products are coming, what is a simplified relation like alpha expression in terms of vapor densities? But this is only when we say the initially the reactant coefficient is 1 and there are gaseous products are coming in the reaction. So for that, alpha will be nothing but D minus D by D into N minus 1. So what is N we say? N is number of moles of are gaseous moles of products. So in this case now, what we had is PCl3 and Cl2 are the gaseous components. So the total number of gaseous products are 2. So here what we got is 2 minus 1, that is 1 as D. So initially we got an alpha expression as D, capital D minus D by small d. Thing clear for everyone? So let us move to the next one. Solid ammonium carbonate dissociates to give ammonia and carbon dioxide as per the equilibrium. Now at the equilibrium, the ammonia is added such that the partial pressure of ammonia at new equilibrium equals to original total pressure. So some ammonia we added, but after that a new equilibrium, because as we add a reactant or a product, the equilibrium might be disturbed. But in this case, because this reactant is like I say, what we generally say, a reaction can be affected, an equilibrium can be affected when we change the active masses of the reactants or products, or maybe the pressure changes or we are doing it, or volume changes we may be doing it. So the equilibrium can be affected by different factors like temperature, introducing inert gas at constant pressure, because whenever you introduce inert gas at constant volume, there won't be any change in or any effect on equilibriums. That you just remember. But when inert gases are added at constant volume also, there won't be any change. So only when it is added at constant pressure, it will be affected. So for that, we just say if ammonia is added, then this reaction, because you will say the partial pressure of the ammonia changes or active mass of ammonia changes immediately, which was at equilibrium initially with a particular pressure or concentrations. So the reaction moves backward because the partial pressure of the products are affected or increased. So the reaction moves backward. This is what we generally use with the K expression with the reaction quotient. That is, if reaction quotient, what you say is, it's nothing but active masses of products to active masses of reactants at any conditions. Means even at equilibrium, even other than the equilibrium position. So when we consider this at equilibrium situation, your reaction quotient Q becomes equal to K. But when it is more or less, then the reaction always tries to attain the equilibrium situation. Because all reversible reaction after an interval of time, after a certain period, they reach an equilibrium situation. So what happens is, when Q is equal to K equilibrium, reaction always remains at equilibrium. So even if you just change the concentration such that if your Q value remains equal to K value, there won't be any effect on the equilibriums. That is how we explain the different factors also. But if Q is less than K equilibrium, then reaction moves, Q tries to become K. So Q value has to increase. So reaction moves in the terms of forward direction because it has to increase the active masses of the product. That means even it will decrease the active masses of the reactants. So you can't say only product's active masses increases. Product concentration increases. So we'll say when a reaction moves in forward, the product value will increase and the reactant values will decrease. Similarly, the reverse situation. When Q is greater than K equilibrium, the reaction moves in backward direction. So when we added some ammonia here, the reaction proceeds backward. So let us say we don't know what is the initial conditions also here. But when ammonium, this one carbonate, carbamate is decomposing into ammonia, what will happen? So if we just write here itself, suppose initial situation, because it is anyhow it's a solid component, we take the solid active masses always as unity. So what we say is we don't write any expressions always for the solid components. So some moles of ammonia you are getting in the vessel at a particular temperature, everything it is fixed. So what we see, we take the only pressure component, suppose, because all that mentioned in the pressures here. So what we say, some moles are formed, they exert some pressure in that particular vessel at that particular temperature. So I say if x moles are coming here, or now let us say 2 is their coefficient, 2x moles of this is coming, they exert a pressure of 2p, it exerts a pressure of p, because you will get 2 moles of this and 1 mole of this, so it exerts a pressure of p. So what is your initial pressure was, that is the initial pressure or initial total pressure is 3p. Then what we said is, what was given in this here, there is some ammonia is added, clear, but a new equilibrium which reaches, there the original total pressure becomes equal to the partial pressure of ammonia. So that we added how much we don't know. So we added some A pressure, let us say. But when we added this, the reaction starts moving in backward direction. Clear? So that how much of this has to react? 2x has to react, let us say, according to the stoichiometric. So the pressure of ammonia decreases by 2x. So simultaneously the pressure of this has to decrease by x. They react in 1:2. But what is given? This 2b plus A minus 2x value is equal to, that is 3p. But what we need is, we need the ratio of total pressure now to the original. So what is total pressure now? You can say directly as 3p, that is the partial pressure of ammonia plus partial pressure of carbon dioxide is the new pressure at the new equilibrium. So what is we need to calculate is only this p minus x value. So how to calculate that? Already we have a initial condition, there was a pressure of this ammonia was 2p and the pressure of carbon dioxide was p. So at that situation we calculated suppose Kp. Then what is Kp was for this reaction? Kp for this reaction will be, if you take with the initial conditions, there is a pressure of 2p for ammonia, that is 2p, that whole square, partial pressure of ammonia whole square, because coefficient of that is 2. Then partial pressure of carbon dioxide, that is p. So what is this is 4p cube will be the Kp. But again, K values always changes only with changes in temperature. They don't change with the pressure changes, with the concentration changes, with the volume changes. So equilibrium constant, which is already we said in the first case itself, first problem already, it's a ratio of the rate constants. Rate constants always affected when you change the activation energies, otherwise only with the changes in temperature according to Arrhenius equation. So what we say? This Kp value should remain same. So what is at the new situation is, it's nothing but Kp, that is 4p cube, should be equal to partial pressure of ammonia square, that is nothing but already we are saying it is 3p, total this value, because there are so many variables for us, it's difficult to obtain those all variables. So let us say this is nothing but now 3p whole to the power of 2 into the partial pressure of carbon dioxide, that is p minus x. So we will get the p minus x value now simply, or you can say partial pressure of carbon dioxide we will get, instead of writing this way you can say it's a partial pressure of carbon dioxide only. So what is this now? It's nothing but 9. So it is p square will cancel. So it is nothing but partial pressure of carbon dioxide. Instead of this you can say it's partial pressure of carbon dioxide. So what is partial pressure of carbon dioxide will be? Partial pressure of carbon dioxide is nothing but now, it's a p will be remaining here, p square you cancel it. So 3 square will be there. So that it is 4, this is 9. So it is 4p by 9. So now what we need is, we need the ratio of new equilibrium pressure to original equilibrium pressure. So what is that ratio he gets saying is A by B. So what is, let us see, we had a space here, use that. So what is new pressure? New equilibrium pressure is nothing but 3P, pressure of ammonia, that is 3P, plus pressure of carbon dioxide, now we got as 4P by 9. So it's nothing but 27 and plus what, 4, 31 by P, sorry, 9. So what is now we want is A by B, which is nothing but the new pressure to the new initial pressure, initial original pressure. So which is nothing but now 31P by 9 by 3P. So it is 27, sorry, 31, 31 by 27. So what is A plus B? So A plus B will be coming up. So it's nothing but 58. So what was the situation is, when we wanted to derive the different variables are there, try to think about in a sense how we can obtain these let us say pressures and everything. So just once go through here carefully. This 2P plus A minus 2X value is a P, 3P. So if we try to solve it as A minus 2X value or anything, the unknown quantities are so many. So that try to minimize these variables. So what we have done is, instead of calculating this P minus X also, you can say directly it is the better as partial pressure of CO2. So that we directly get partial pressure of CO2, partial pressure of ammonia, we know already it is a 3P. Clear? But only the way how the reaction proceeds, for that purpose only we have written this, but we don't use anywhere, or we can't use this anywhere to get the solution here. Okay? So that is now coming to this. So it's a simultaneous equilibrium question now. So when there is a simultaneous equilibrium, means in a reaction vessel itself, we have 2 or 3 equilibriums existing at a time. Then what happens? Any component which is there in 2 or 3 reactions, suppose, in 2 or 3 equilibrium, suppose, the active masses, whether it is a concentration, pressure, moles or anything, whatever we take, these active masses should remain. For every equilibrium it should be same, because for particular reaction you can't have that partial pressure or particular molar concentration to maintain that equilibrium and this equilibrium, because all that B or A or a particular component is there in the completely vessel. So what we have to do is, we have to always consider it as the pressure or any active mass thing what we take, it should be always same for all equilibriums. So here what is this now? See. So we have taken these 3 equilibriums. B is a common component in this, B is here also, B is in this also. Similarly, A is in this, only D is not there in the 3. So D is an individual. Means what we have done is, we started this equilibrium already is saying in the numerical also. Initially started with A, B, D, because your initial reactants are A, B, D. So A and B are maintaining this equilibrium with C. B and D are maintaining an equilibrium with E, and B and A are maintaining this equilibrium with F. So, but what is given? Let us see. There are 3 which are simultaneously there, but he gave the number of moles of C, E and F. So how many moles are there at equilibrium? So at equilibrium, at every situation, let us say it is equilibrium situations, we have 3 moles of this, 2 moles of this and 4 moles of this. But when a reaction exists, reaction takes place. Suppose we started with already he is saying 8 moles of this, 8 moles of B and 2 moles of this. So here also there should be 8 moles. Here also there should be 8 moles. Here also there should be, sorry, this is 8, this is also 8. A and B are 8. But now what we say, for this reaction, some amount of A and B has to convert into C. So how much will convert? Maybe some X will convert, let us say. Suppose we use a variable like X here. Here also how much has to consume? 2X has to consume. So simultaneously what happens is, immediately everything changes here. So this also becomes 2X immediately. This also becomes 2X immediately. This also becomes 9, again 8 minus X. So now, how much of this you will get? You will get 3X. Means your 3X value is nothing but equal to 3. So that means here you will get X is equal to 1. Coming to the second reaction. What is second reaction? We are saying it. That is B and D are simultaneously reacting now to E. So how much of this may react here? So for this reaction, some amount of B has to react again. So how much may react already? Already 8 minus 2X is there. So that now let us say Y reacts. So I write with the specific things now. So it is 2Y is reacting here. So that simultaneously this becomes 2Y. But how we will say this is already you said 2X? They are variables. So they get adjusted in a particular the Y as it is consuming here or the B is reacting in this reaction. Accordingly this X will react. So what is effectively what we have is the X value is remaining 1. So it was not X which is 1, where 8 minus 2X is there. So all are only simultaneously there. So effectively some amount of A or B reacted in this case with an X value that is equal to 1. So here how much of D has to react? Their ratio is 1:1. So this also Y. So how much of this we should form? 2Y. That means now 2Y value is equal to 2. That means Y value is also equal to 1. Now coming to like here also you can say this is Y. So all B at any equilibrium should be same. Now coming to this, the third one. So what we had here is now for this equilibrium, B and D, B and A again has to react. So A and B are maintaining with C as well as A and B are maintaining with a different stoichiometry, maintaining with F, another equilibrium. So how much of this has to react here in this case? So let us say here 3 and 2 ratio. So it is let us say 3Z. Here again it should be 3, 2Z. So you can change immediately. This is nothing but 3Z B. This is also 3Z. So that your X and Y, Z, all are variables. They get adjusted with one another to maintain all the three equilibrium simultaneously. So at any situation, the B will be 8 minus 2X minus Y minus 3Z. Similarly this. Similarly this. This is 2Z. So how much of this you will get now? When this is 3 and 2, we will get 4. Means 3Z and 2Z are reacting to give 4Z. Means this is again equal to 4. That means Z is again equal to 1. You can use any variables. So now what is X, Y, Z values? We got it. All are 1. So what is the effective value of A will be? Because what we need now is the Kc for the value equilibriums. So for each equilibrium we have to calculate what is K. So what is A value? X is 1, Z is 1. So 1 minus 2. That means nothing but it is 1 minus 2. That is nothing but 3. So 5. So here also it should be 5. What is A? This 8 minus 2Z, 2X minus Y minus 3Z. So this is 2, this is 1, this is 3. So 2, 1, 3. So that it is nothing but 6. So this value is nothing but equal to 2. So the C value is already known 3. So what is this pressure of this is, or concentration of this is 2, concentration of this is nothing but 5, concentration of C is nothing but 3. So what is equilibrium constant I can write now? So for first equilibrium, K equilibrium will be, it's nothing but 3 cube C cube by A, that is 5, into 2 square. Clear? Now coming to the second things, second equilibrium. So this is again nothing but directly 2. What is this? Nothing but 2 minus 1, that is 1. This is again anyhow will be 2. So what is K equilibrium for this? Kc for this, or K equilibrium for this? Because all are in 1 liter container also. So there is no change in the concentration, because already number of moles by volume will give concentration. So directly I use, they are the like concentrations here, because why you have taken 3 maybe. So you have to take actually the moles by total volume, that will give the concentration, because it is 1 liter container. So there is no issue for us. So now what is K equilibrium in this case? What is K equilibrium here? It's 2 square by this is B, that is 2, into this is 1. So what is in this case? So this is again already we say this is 2 also, this is 5, this is 4. So what is K equilibrium for this? It's nothing but 4 to the power of 4 by 2 to the power of 3, and this is 5 to the power of 2. Clear? So it's only again solving it, and we can proceed that and calculate what is this is already 2. You can say this is 2 square by 2, this is 2, this is 27, this is 20, 27 by 20. So directly it is nothing but 27 by 20. This is nothing but 2. This is 4 to the power of 4. So it is nothing but 16, 64, 64. So 16, 16, 256. This is 8 and this is 25. So 25, 8 times, 25 8 times is nothing but 25 4 times is 200. So it is 8 times. So it will be nothing but 200. So it is 256 by 200. Clear? Now, so only thing, the simultaneous equilibrium, all components concentration should be at every situation has to be same. This was the space was there. Now, this one. So there is a AgCN2 complex with Ag plus and 2Cn minus, maintaining let us say dissociation constant. So we always simply you can say any complex formation, their equilibrium constants will be very, very high. Their dissociation constants are always very, very low. So what we need is now Kc, the Kc at this equilibrium, for this equilibrium is given. Calculate the Ag plus in solution, which was originally in a 0.1 KCN solution and 0.03 AgCN, AgNO3 solution. So originally we had actually silver nitrate and KCN. But this Ag plus and cyanide ions, they are forming the complex. So ionic equilibrium, you can just do this simple, let us say approximations here. So let us take the equation in the reverse order. I say as Ag plus 2Cn minus. This is in equilibrium with Ag, Cn twice minus. But whenever there is a complex formations like this one, we said K equilibrium when it is taken for this equilibrium is very high, as I said just now. So how it will be high? Because when we write the any equilibrium in a reverse order, your equilibrium constant which is given in this direction, if you take the reaction in the reverse order, your equilibrium constant will be reciprocal of that. So what was the equilibrium constant for this will be? K equilibrium or Kc for this reaction will be nothing but 4 into 10 to the power of minus 19. in the denominator. So that it will become now as 10 to the power of 19 by 4. So it's very high value. So what happens immediately? When it is a higher value, the reaction has more ability to move in forward direction only. So how much of this we have taken? 0.03. And how much of this is there? 0.1. So this is, let us say, we write this as 0.03. This is 0.1 initially. This was initially 0. But when a complex is forming, it completely tries to move in the forward direction. But as per the given conditions, if you see, they react in 1:2 ratio. So here we are given 0.03, this is given as 0.1. So for 0.03, how much of this will react? Double to that is nothing but 0.06. So we say this is completely limiting reagent as far as the stoichiometric applications. So that you will say anything which is limiting, it completely transfers into that form. So I say this completely Ag plus concentration moves into that stage, means it is nearly 0.02 something 9999 will be there, so that your value of Ag plus will become, as equilibrium is there, some Ag plus has to be there. So there is a negligible amount of Ag plus might be there. So that this Ag plus, which is 0.03, completely converts into this form. So I say this is 0.03. This is the simplest approximation what we can say based on the equilibrium constant values. So if equilibrium constants values are so high, you can say which is limiting, that completely transforms into the product side. Maybe this is also nearly going like that. So how much of that is going? This is 0.1. For this 0.03, 2 times of that has to consume. That is 0.06 consumes. So how much of a Cn minus will be there? That is 0.04. So some Ag plus will be left. So you can write as Ag plus or you can write an X. So what we need to determine is now the Ag plus concentration at equilibrium when this complex formation was there. Clear? So what is now equilibrium constant in this direction? We have taken as 4 into 10 to the power of minus 19. You can take like this also. It's only to just say, because calculation anyhow we have to calculate Ag plus. So what is this value? Concentration of this, that is 0.03 by Ag plus, that is directly, let us say Ag plus only, then cyanide whole square, that is 0.04 whole square. Clear? So this will be, you can say 1 10 to the power of minus 2, you can cancel from these two. 1 10 to the power of minus 2 will be left in this. So what is Ag plus overall is? Ag plus overall concentration should be now. It's nothing but 1 of the 4 I can also cancel. So 1 4 is left. 4 into 10 to the power of minus 2 is left. So you can take there. So it is 4 into 10 to the power of minus 2 by 4 into 10 to the power of minus 19. Clear? Okay, Ag plus comes here. So it comes to numerator. Sorry. So it is 4 into 10 to the power of minus 19. So Ag plus comes here. This comes to numerator into 3 because we cancelled 1. So that it is 4 into 10 to the power of minus 2. So this 4 cancels. It's nothing but 3 into 10 to the power of minus 17. So what was the concentration of Ag plus might be? It's a 0.0003 somewhere. Let's say after 10 to the power of minus 17 decimals. Clear? So it's a very low concentration. So that we said approximately it is converted into that. Next part. The degree of dissociation of HI at a particular temperature is 0.8. Then he is asking the volume of Na2S2O3 hypo sodium thiosulfate, which is required to reduce, means which is required to, let us say this is a redox reaction between hypo and iodine. So whenever there is an equilibrium mixer, sometimes there are some components given which might be only reacting with one of the component in that, so that we can get that component concentration. From that we can able to determine the others concentrations, other active masses, so that we can calculate Kc expressions, means Kc values or Kp values or anything like whatever we write in terms of some amount of this has consumed for the reaction to attain equilibrium. So, in such a situation, now what we say is sodium thiosulfate reacts only with iodine and it reduces iodine. Like we just say this is a standard reaction in iodometry titrations. So, sodium thiosulfate reacts with iodine, converts into Na2S4O6 plus NaI. So, if you balance it is 2, this is nothing but again 2. That means 2 moles of this reacts with 1 mole of this. So, we are given the concentration of sodium thiosulfate, we need its volume in liters. So, that let us see what is the equilibrium. That is, we have taken H2 and I2. So, H2 plus I2 which was in equilibrium with 2Hi. Now, the 2 moles of this and 2 moles of this is taken and volume is given when such reactions are given like H2 plus I2 2Hi. Volume actually does not affect the equilibrium values, equilibrium constant values. You can even neglect that volume values also, because for this type of reaction where delta Ng is 0, for such reaction there is no influence of volumes. So, even you write a volume applicable values or anything, that has no affecting the calculations or anything like that. So, initially we have taken 2 and 2, this was 0, but to attain the equilibrium again H2 and I2 has to consume, because it is when it is heated in a vessel, closed vessel, and to attain the equilibrium. So, 2 minus x of this, 2 minus x of this might be there, because x is reacting, I say. I do not use alpha. If I use alpha, what I should write is 2 is the moles that are present. Alpha will be the number of moles that will be reacting for 1 mole. So, that the number of moles that consumes for 2 moles should be 2 alpha. So, that is generally a mistake, sometimes they might be doing it. But if you take alpha value, means use the alpha variable, your value what you write here is 2 minus 2 alpha, that you have to take care. So, better you write x reacts. So, if x reacts, it is better to use the stoichiometric ratios than 2x forms. So, if I can get x value, then I can say then number of moles of iodine. So, how many moles of iodine might be reacting? Then I can calculate number of moles of sodium thiosulfate. Then from that number of moles of sodium thiosulfate, we can calculate the volume, because number of moles should be always nothing but molarity into volume in liters. So, when volume is taken in liters, if you multiply the molarity and volume, it gives number of moles. So, when it is in ml, it gives millimoles, but if it is in liters, it gives moles directly. So, if you can get the moles, you can calculate the volume in ml, liters. So, if you want millimoles, you can say you can calculate volume in ml. So, all the applications you can just see carefully. So, let us see what is this x value, how to determine. It is a problem for us, because we do not have any value given for us, but the initial information which is given, the degree of dissociation of Hi is 0.8. From that I can calculate actually K for this, but it is given for Hi, means you are calculating actually in terms of reverse direction. So, what is that reverse direction is? That is 2Hi is in equilibrium with H2 plus I2, but at the same temperature we are taking the reaction in the reverse direction. Means whenever suppose temperature is not mentioned, suppose here particular temperature is said. So, at a particular temperature, okay. If suppose something temperature is not also mentioned, then you just say whenever the temperature is not mentioned in the applications, you can take the temperature value constant. Means that at the same temperature the applications are asked. Like, clear? So, this is 1 initially, let us say this is 0 and 0. He said 0.8 is the degree of dissociation, that is why we are taking the initial moles of Hi as the 1. So, what is degree of dissociation? Is alpha as 0.8. So, this is nothing but 0.8 moles reacts in this. So how many moles of this will be left? 0.2. So I subtract 0.8 from here. So I will get 0.2 moles of this. But if this is 0.8 is reacting, how much of this has to get? 0.4. This is also 0.4 because for 2 moles you are getting 1 mole. So this is 0.4, this is 0.4, this is 0.2. So what is Kc for this reaction in this direction at this temperature will be? It's nothing but 0.4 into 0.4 by 0.2 into 0.2. So one of that 4 you can cancel in this. Anyhow, point will go. Kc for this reaction in this direction is 4. So in its reverse direction, what we are considering here, it should be nothing but now 1 by 4. So what is this 1 by 4 now? Here is nothing but 2x whole square by 2 minus x whole square. So in such situations, don't try to calculate in terms of squaring the things and do, because it is the square of a particular value here 1 by 2 whole square. So it's 1 square, 2 square, nothing but 1 by 4 only. So if you write this as 1 square by 2 square, means you take the square root on both the sides. It's nothing but now 2x by 2 minus x is equal to 1 by 2. So this becomes now 4x, this is 2. So what is x value what you get from here? X value what we get from here is nothing but 2 by 5. Just see, this is 2 minus x, this is 4x, this x comes here and becomes 5x. So its x value is nothing but 2 by 5. So if x value is 2 by 5, how many moles of iodine we exist? 2 minus 2 by 5. That's nothing but, this is nothing but you can say even as a 0.4. Okay, so this is nothing but 0.4 or 2 minus 0.4. Otherwise you can write here as 0.4 here. So this is 0.4, so it is 1.6. So when you have 1.6 moles of this, how many moles of this has to consume? 2 into 1.6. So if we just use now number of moles of sodium thiosulfate is 2 into 1.6. Molarity is given as 1.6 into V, that what we require. So what is V now? Is nothing but this 1.6 cancels, V will be nothing but 2. So the volume of the sodium thiosulfate that is required for us is nothing but equal to 2 liters. Clear? So we are measuring the equilibrium constant and we used that equilibrium because from the initial information we use that equilibrium constant value and we measure what is the amount of iodine that exists. Clear? Now, this one. PCl5 dissociates according to the following reaction. At equilibrium, all the species have 2 moles each. Then find the number of moles of Cl2 that is added at the equilibrium so that the pressure and temperatures are same, but the volume of the container becomes double with respect to initial. So if you take PCl5, PCl3 and do let us say from the initial what is given for us at equilibrium already which is reached, this is 2 moles, this is 2 moles, this is 2 moles. We don't know volume given, volume of the container is not given. So let us say it is V. So I say concentration of this becomes 2 by V, concentration of this becomes 2 by V, concentration of this becomes 2 by V. So what is Kc for such reaction now? It's into 2 by V into 2 by V by 2 by V, which is nothing but overall 2 by V. But we added some Cl2. Then the reaction starts moving in backward direction. That means number of moles will decrease actually. But he is saying there is some twist in the problem actually. Means we just generally say the PCl3 and Cl2 are consuming and PCl5 is forming. Number of moles are decreasing. How the volume is increasing? Clear? So, if you just again take variable of the Cl2, how much of Cl2 is added. So, what I do is, I just erase this thing and utilize the same thing for the next calculation, let us say. So, already there are 2, 2, 2. We added some moles of this. So, how many moles of this we added? Let us say again A, general number or X or something. But reaction has to move in backward direction. Means we added the number of moles of Cl2 in such a way that even the number of moles in the gas equilibrium mixture might be decreasing, the total volume of the vessel is increasing. But pressure and temperatures are given as constant. So what do we say? Here this might be X is reacting, here X is reacting, you will get 2X. So what we say, total moles at equilibrium maybe. Means we have to calculate now, only thing is, what we have to see is, find the number of moles of Cl2 that added. Means we have to calculate this A value. How many moles of Cl2 we added. So let us say total moles at equilibrium once. What is this? This is totally 2, 2, 2, 6. This X and this X will go, this X will remain. So A plus X value, we got it. A minus X, sorry. These are the total moles at equilibrium. Now, but what is given as an hint, because X value we can't determine from here, because even if you take the volume as 2V, its concentration should become 2 plus X by 2V. Its concentration should become 2 minus X by 2V, because he said volume doubles. It is 2 plus A minus X by 2V. If you substitute in this, you have two variables. So try to minimize the variables. That is the main important thing. So what we see, there is one twist what we use is, using ideal gas equation, that is equation of state, PV is equal to nRT. Then that is nothing but pressure and temperature are anyhow constant. We say volume is directly proportional to moles. So when there are initially 2 moles of each one, we had a volume of V. Now when the volume becomes double, your total number of moles also should become double. So when the number of moles are initially, when it is V, it is 6. Now at final situation, after attaining its 2V, should be now equal to, let us say 12. It should become double. Means the total moles at equilibrium should be, means this 6 plus A minus X value is equal to 12. That means A minus X value is nothing but 6. Clear? So we already say this is now as totally A minus X. You write here as 6. So this becomes 8. Now we can determine only there will be one variable, X only, because it is 2 minus X, this is 2 plus X. So that it is now already Kc values are known 2 by V. So what is now we do, let us say, at this, what is concentration of this? It's 2 by V, it's 2V, this is 8 by 2V. So what we write as Kc, 2 by V is equal to 8 or 2 minus X by 2V into 8 by 2V by 2 plus X by 2V. So we will get an X. That X if I substitute here, then I can get what is A. So what is this now? One of the 2V you can cancel, this V you can cancel. Clear? So that it becomes now 4 also you can cancel. This 2 you can cancel. Completely like this. So overall whatever is there is, this is 2, this is 2 plus X. So this is nothing but 1 is equal to 2 into 2 minus X by 2 plus X. So what is X? Overall you will get. This is 2 plus X. See carefully. This is 2, this is 2 minus x. So this is 2 plus x is equal to this. This is 4 minus 2x. So if you take 4x here and 2 here, so it is nothing but now 5x, or x is equal to nothing but, this is 4, this is 5x on this side. So 4 by 5. Clear? Nothing but 0.8. So if it is 0.8, then what is A? A minus 0.8 is equal to 6. A is equal to 6.8. So total overall moles of Cl2, what we should add to the equilibrium already attained with 2 moles of PCl3, Cl2 and this is nothing but 6.8. So higher quantity what we added, so that even the reaction moves in backward direction, you will be attaining the situation where the volume of the container also becomes double. Clear? Now, okay. Now this one, like a matrix, like previous IIT exam question, I think. So such type of questions have come. So carefully understanding the graphs and giving which is a proper option for each graph. So 1, 2, 3, these are mentioned here, is nothing but your A, B and A to B, or A and B to and A to B. Let us see what is this reaction. Is an endothermic reaction. So already we started with A, that actually it looks like A and B2, and concentration of A to B product is 0. So it is increasing, these two are decreasing. So what is this is representing? This is representing for A, 1, 2 is representing for B2, because the ratio in which they are reacting is 4:1. So the A value should decrease more and B2 value should decrease slowly, because 1:4 ratio they react. Means if X reacts here, 4X has to react in this situation. So what you see, this is nothing but A to B. So in every situation it is like that. So what is now? Already this stage is an equilibrium stage. After this, concentrations are decreasing, increasing, something like that. So if you just see first one, immediately after reaching the equilibrium, you are seeing the concentration of A, B2, A to B, all are falling immediately. When it will fall? Means if the reaction is endothermic, if you suppose increase the temperature, reaction moves forward. That means A and B2 has to decrease. A to B should not decrease. Clear? Because A to B concentration should increase. Then immediately when increasing temperature is there. So what we say, at this situation or in this condition, the concentration of all the species should not be decreasing. Because reaction, as you start increasing the temperature, reaction starts moving in forward direction. So A and B values or A and B2 values are starts decreasing, A to B value starts increasing. So immediately they reach an equilibrium again. So till the concentration values are attaining, let us say the ratio of active masses of product and reactant attaining a particular temperature which we reached. At that situation, what is the ratio that it has to maintain? Because it won't maintain the original value, it will maintain a new value. And when the reaction is endothermic, its equilibrium constant always increases. Means it moves in forward direction more, products amounts will increase, reactant amounts will decrease. Like even we have the Van 't Hoff equation to prove it. Clear? So that is not correct anymore. So this is not correct. Increase in pressure. So when you increase the pressure, immediately the partial pressure of each components will increase immediately. So at that situation, the number of moles are already there. So if your total pressure is increasing, your equilibrium moles which are already there at a new equilibrium, their mole fractions remain same, but you are increasing the pressure, so immediately their partial pressures has to increase. So what is the situation is, if you just observe this B option, A pressure is immediately increased, B pressure is immediately increased, or concentrations are immediately increased. That means indicating this increase in pressure will be nothing but this. Satisfies this situation. Clear? Oh, sorry, this is increasing slightly, this is increasing slightly. So, this is, let us see, addition of A to B. So, A to B at equilibrium, if you are adding, only A to B value should increase. This is what is increasing. So, this is indicating for R. Now, addition of inert gas at constant pressure. Whenever any equilibrium reaction where delta Ng is not 0, so for this delta Ng is not 0. That is, it is 4, this is 1, this is 2. So, delta Ng is for this reaction is not 0. So, in certain situation where delta Ng is not 0, if you are adding an inert gas, the reaction always moves in a direction where number of moles are more. Means for this reaction, suppose if we add an inert gas at constant pressure, then equilibrium has to move in backward direction. So, here then what should happen? A to B should decrease, A to B should decrease, and immediately and A and B2 value should increase. So, where it is now? A to B is decreasing. When inert gas is added, reaction starts moving in backward direction. So, it is increasing, this is decreasing, this is decreasing. So, no, this is increased, this is increased, this is increased, no. Clear? So, this is also indicating, this also Q also indicating this. This is okay, little bit changes are there. So, I think this might be there, let us see. So, here you can say this is more appropriate for Q actually, this is more appropriate for Q because all partial pressures will increase, A to B, A, B will increase, but this is satisfying this to some extent. Sorry, this is also not satisfying. This is also not satisfying. Just a minute, we will see this one later. So, A to B is increasing. So, no, A to B has to decrease. So, where is decrease? Here it is only decrease, but A to B, then AB also should increase. That is also not there. So, for this, let us see which one will be satisfying. Next, this situation when it is increase in volume. So, when volume is increased, concentrations will decrease. So, this one satisfies this case. Clear? So, when we introduce the inert gas, there is one more thing maybe, that is partial pressure of gases, because mole fractions immediately decreases. So, at constant pressure, moles are increasing, number of moles are increasing, so partial pressures will immediately decrease. So, this also satisfies for S. So, first graph satisfies for S and T. Clear? So, let us erase these things. Then second graph satisfies for, now what is that? With increase in temperature, immediately that is increasing. So, this B is satisfying for that. So, let us see now, this is what we see for, this is for P, this is satisfying for R, I think, this was satisfying for Q or something. So, already just what we did, see. So, with the increase in pressure, then immediately all partial pressure. So, this is satisfying for Q, this was satisfying for Q, and this was satisfying for R. So, with A to B is added, A to B concentration will increase, AB concentrations will. Clear? So, A to B is added at equilibrium, its concentration should immediately increase. So, this will satisfy for R. So, let us see what is that answers already. Clear? So, this ST, this is satisfying for R at equilibrium AB value. Okay, sorry. This is what we. So, A, this is satisfying for R, this is for Q, this is satisfying for now P. So, when you increase the temperature, AB value should decrease, A to B value should increase. So, when we added an A to B immediately increases, A and B is not affected nearly, but A to B starts decreasing, A and B starts increasing. So this has to be R, just a little bit. Okay. Now, so these are the questions which were discussed till now, are from to say chemical type equilibriums. Now we have most of the questions now related to the ionic equilibrium, pH related. Let us say we are measuring for buffers or hydrolysis, KSPs and ionic equilibrium. So the calculations of salt hydrolysis, pH or acidic basic buffer, acidic basic mixtures, for that we are actually trying to do. Now where is H3PO4 at particular volume and concentration, we are trying to neutralize with sodium hydroxide. We added different volumes of sodium hydroxide. Then what is the pH when we added 0 ml, means we have not added anything. Then it is 50 ml, then it is 100 ml, if it is 150 ml, if it is a 200 ml. But as we see, the H3PO4 is a tribasic acid, means it has dissociation in 3 stages. So it gives first an H plus, then another H plus. So if you write H3PO4, that is H3PO4 is in equilibrium with initially with H plus and H2PO4 minus, which is what we say Ka1. The values of pKa1, pKa2 values are given. Then this H2PO4 minus is converting into H plus and HPO4 2 minus. Then this HPO4 2 minus is converting into H plus and PO4 3 minus. But in a polyprotic acids, which can give ability to give more than one, their further dissociations always will be because of what we say as common ion effect. Since already H plus is coming, the H plus always influences the degree of dissociation of others. So the degree of dissociation of this is less than this. Degree of dissociation of this is less than this. So the Ka values will continuously decrease. So pKa1, pKa2, pKa3 values are always increasing because Ka value increases, Ka value decreases, pKa values will increase. So first, when we take the H3PO4 and try to add some NaOH, then it tries to convert into NaH2PO4 first. So how many milli equivalents of this is taken for us? 0.1 into 50. So when it is not added, directly we can do, because it is only H3PO4. So what is the initial pH will be, that we will do. So let us see what happens, let us say at each situation. So we had 0.1 of this, we add some volume, but equivalence has to be equal, means at 50 ml, means V is equal to 50, these two are equal. At 50 ml, you will see the formation of this. But we say it is a salt of H3PO4, clear? So that when we take this component, this can undergo hydrolysis, because a component which is coming from a weak electrolytes, anion, cations, which are coming from a weak electrolytes, they undergo hydrolysis. A component which is coming from the strong electrolyte cannot undergo hydrolysis. So sodium ion is coming from strong electrolyte. So how do we say NaOH is a strong electrolyte? Because whenever there is a equilibrium constant, when it is a weak electrolyte, equilibrium constant for that component will be mentioned. It's the simplest hint for us in anionic equilibrium. So if an acid is weak, its Ka value will be given. If base is weak, its Kb value will be given. If it is salt, then its KSP values are given. It's a salt in the sense when you are dissolving it in water, then its KSP value will be always mentioned. When it is, let us say, a component which is coming from a weak electrolytes, then it is cation or anion which can undergo hydrolysis. Their KH values will be given, or Ka values will be given. From that we can calculate what is its KH values. So here first it will convert into this, means at 50 ml it converts into, so at 50 ml you will say it converts into NaH2O4. At 100 ml what happens is, this is, if you take 100 ml, then it is 0.1 into 50, this is 0.1 into suppose 100, this completely converts into, means it is two equivalents, what we added, 2 moles what we added, this is 1, so it is 1:2 ratio, so that you will see Na2HPO4 formation. So here at 100 ml, you will see formation of Na2HPO4. And at 150, it is 0.1 into 50, because already it is converted into this, this is converting again back into this also you can take, but it is also one way, other way, 0.1 into 150, it is giving now Na3PO4. So at this situation, we have Na3. So when you add 200 ml, it's nothing but your acid is completely, H3PO4 was completely neutralized at that situation, and it's completely mainly Na3PO4 and excess of NaOH, because at 150 that H3PO4 was completely neutralized. So at these situations, what is your pHs? So what is initial pH? So for any weak acid, it's a simple condition to use directly to give what is its pH values. So let us say at first condition A, at 0, 50, 100, 150, it's a 50, 50. So let us say first one A, at 0 ml, addition of, means only H3PO4 is there. So what is the H plus concentration at this situation for a weak acid C? We can directly use a simple relation as under root of Ka1, because the H plus coming from only the first dissociation will be affecting it. So your approximated values we are trying to measure. If you want to calculate exact, then you can say what is the value of H plus concentration, you can use it and calculate. And saying it, suppose this is initially H3PO4, we have 0.1 here, we have X reacting in this, you will get X and X. So you can say X square by 0.1 minus X, you can use it and calculate. So let us say what is Ka value, it's 2.1, pKa value 2.15. So you have to use those log values and calculate. That is one way. So but you suppose neglect X, then you will get that simplified relation what I am trying to give. Otherwise, what is the other way of actually doing it? Okay, this we take. So what is the thing what we can do? So it is Ka1, which is nothing but 10 to the power of minus 2.15 is equal to X square by 0.1 minus X. So if we want an exact way of determining, we can determine like this, but this you can say as anti-log of, whenever it is points minus fractional values, you can take this, you are subtracting from 1, so you will get anti-log of 0.85, and this is minus 2, you can increment 1 unit as 10 to the power of minus 3. So what is 0.85 anti-log? Maybe. So we just suppose go log 2 is 0.3, log 3 is point like that. We go on doing it, where you get, like to say, log 8. Log 8. So log 8 will be nothing but 2 cube. So log 2 cube is nothing but 3 into 0.3. So it is 0.9. Means this value is around 8 point something. 7 point something. Sorry, 8 is already 0.9. So it will be 7 point something. So you can say anti-log of this will be around 7.2 into 10 to the power of minus 3. So is equal to X square by 0.1 minus X. So from here you can determine X, and your H plus concentration will be only from this dissociation initially. So that you can use it and calculate pH. Clear? Otherwise, if it is low value, your initial values are even suppose low, you can say initial pH will be like this, you can determine. So what is the initial pH that you can determine? This we'll see the graph later. So what is initial pH you can take? It's a Ka1 into C. So maybe approximated value you will get, but not exact, because in this case when the all K values are not so low, you can't neglect that 0.1 minus X as 0.1. So you can't write that one in the previous equation what we had. So what we see at 0 you can determine through this, otherwise half into you write pH is equal to as pKa1 minus log C. Maybe if it is an approximation then you can use it, but in this situation you should not do that because it was not the negligible, because K value is not so low. But what is second situation? When 50 ml is added, it was Na2H2PO4. So it's a salt of H3PO4. But H2PO4 minus undergoes hydrolysis. So for H2PO4 minus, when it is hydrolyzing, it is converting as H3PO4 plus OH1. What is its hydrolysis constant, that is KH is? Whenever the anion is undergoing hydrolysis, that anion which is coming now because of the first dissociation of H3PO4, your KH is nothing but Kw by Ka1. So if you take the let us say simplest expression for a salt of, let us say this is a weak acid and strong base salt. What is the general expression we have for a salt of weak acid and strong base is pH is equal to 7 plus half into pKa plus log of C. But what is this C? It's the concentration of the ion which undergoes hydrolysis. So what is that ion here? It's nothing but H2PO4 minus. But what is this Ka? It's the first ionization constant, that is Ka1. So what is pH at this situation? 7 plus half pKa1 2.15 plus log of the concentration of this. How much of this you will get? 50 mLs are required. So how much of this you are getting actually? 0.1 into 50. But the total volume after addition for 50 ml and 50 ml of NaOH becomes 100. So the concentration of this will be nothing but it is 1 by 2, that is 0.1 by 2. So you can say this is nothing but 0.1 by 2. So from here you can calculate what is its pH. And second, the C, we have suppose 100 ml, but already we said it's nothing but Na2HPO4. So that we say it's nothing but now as this is hydrolyzing again, but when it is second anion, so what is again KH for this hydrolysis will be KH for hydrolysis, this will be nothing but Kw by Ka2, because here HPO4 2 minus is undergoing hydrolysis. So what is KH again? You can say what is pH here again? It's again a salt of weak acid, like that if you take 7 plus half into pKa2 in this case plus log of concentration of this. What is concentration of this? 0.1 into 50, 0.1 into let us say 100. So that how much you will get, that you can take, that is 0.1 into 50 by totalize becomes 150. You can write that concentration here. So what is this will be? 0.1 into 50 by 150. Because 50 ml of H3PO4 already, 100 ml of H3 NaOH already. So that it is 150. So that you can write here. Then D, the same 150. Then it is nothing but Na3PO4. then it is KH is nothing but again KW by Ka3 in this case. So when you write pH again, it's nothing but 7 plus half into pKa3 plus log of C. What is log of C? 0.1 into 50 by 200 in this case. 150 and 50. So we can even calculate pH. When it is E, when 200 ml is ours, the pH will be, or even though you have Na3PO4, you have NaOH. When a strong base is there, the hydrolysis of this will be suppressed. So your overall concentration, which is OH minus concentration, is the excess of NaOH concentration. So how much of excess of NaOH we have? That is 0.1 into 50 we have taken here, 0.1 into 200 we have taken here. Means if it is H3PO4 plus NaOH, you have Na3PO4 plus 3H2O. So how much of this was there? This is 0.1 into 50. This is 0.1 into 200. But how much is consuming? 150 is consuming. So 0.1 into 50 of this is left. So this is nothing but 0.1 into 50 by total volume. That is 200 plus this. That is 250. Because it's NaOH is in excess. It's the overall OH minus ion concentration. I think clear? So in this way, we can determine the concentrations and pH values at a different addition of NaOH. So if you see the graphically, this one, moving it back a little bit. So if you just see this thing, so what is given here is we added different OH minus ion concentrations. The graphical representation, what we see for the applications is, that is A, B, C, D. These capital letters are nothing but now the pH at different situations. Clear? So if you just see with this is the initial pH, but at this B there is complete conversion of H3PO4 into NaH2PO4 at this situation, at this situation, at this situation, different. So this is the first equivalence point, this is the second equivalence point, third equivalence points, and after that. But in between that is suppose they are asking in between A and B what exists. In between this you have H3PO4 because it was not neutralized completely, and you got NaH2PO4, means it is forming a buffer. At this range there is buffer, in this range there is a buffer. So there are three different buffers existing between the first equivalence point to second equivalence point. It's initial to the first equivalence point, first equivalence to the second equivalence point, second equivalence to the third equivalence point. You will see different the buffer situations. So the first buffer is like this, second buffer is nothing but NaH2PO4 plus Na2HPO4, and here Na2HPO4 plus Na3PO4. So there are different buffers existing. But at these situations, you are seeing the neutralization, first neutralization, second neutralizations. So this is the thing. So we can just do this calculations. Now, when 20 ml of 0.2 m DCl, so we just changed the isotope of hydrogen as deuterium. So DCl means it's like HCl mixed with 80 ml of NaOD, again PD here you are using again, but we need an ionic product of heavy water. So like water, what is ionic product? It's the H plus or OH minus concentration product, or H3PO4 and H3O plus and that. So whatever it is, if you just see what is D2O ionic product will be, that is Kw of D2O will be nothing but D plus concentration and OD concentration. So if you can calculate D plus and OD concentration, we can calculate ionic product. But PD is given, means it's nothing but like pH, negative logarithm of H plus concentration is pH. So here nothing but it is a negative logarithm of this. So what is D plus concentration from this value? D plus concentration from this value, PD is given as 13.6. D plus concentration is nothing but it's 10 to the power of minus 13.6. So what we can take this as 10 to the power of minus 14, as we just said, it's an anti-log of 0.4. It's an anti-log of 0.4. So this will be nothing but now anti-log of 0.4 is 0.3, log 2 is 0.3, log 3 is 0.477. So it should be in between that. So it may be somewhere around 2 point something, 2.5 into 10 to the power of minus 14. Let us say maybe. So 2.5 into that way, let us. Maybe your values are maybe approx. So let us see, this is 20 into 0.2. This is 80 into 0.1. So when you react DCl and NaOD, sorry, we are getting NaHCl plus D2O. But how much of this is taken for us? 20 into 0.2. This is taken as 80 into 0.1. So this is nothing but 4. This is nothing but 8. But this is excess. This is limiting. So this completely gets consumed. So this is also gets consumed 4. So this is 4 is left. That means 4 millimoles are left because volume is in ml. So how much of OD concentration? OD minus concentration is nothing but excess amount of that by total volume. So it's nothing but number of excess millimoles by volume. 20 plus 80, that is 100. That is 4 into 10 to the power of minus 2. So we said D plus concentration is this and OD minus concentration is this, because we are taking it as 10 to the power of 15 or 4 is there. We are using that approximation as log 8.4 as between 2 and 3 as an exactly half we are taking. So what is Kw of D2O? D plus 2.5 into 10 to the power of minus 14 into OD, that is 4 into 10 to the power of minus. So it should be 10. Clear? So this is 10 to the power of minus 16. So it will become 10 to the power of minus 15. Clear? So we need to determine only the D plus and OD minus concentration. So here in excess of NaOD was added. So the NaOD was left. So OD minus concentration we can obtain from here. And both these are now considered to be the strong DCl because K values were not mentioned. So directly we can use it and do. Let us see the next thing. The amount of ammonium sulphate in grams which must be added to 500 ml of 0.2 MnH3 to yield a solution of pH 9.3. pKb of ammonia was given. So what it indicates, ammonia is a weak base and we are getting it salt of ammonia from H2SO4 because it is ammonium sulphate. So it's a ammonium sulphate is nothing but a salt of strong acid weak base. So what is the pH expression that we can take? Directly let us use it, because it's a strong acid and weak base, pH should be less than, clear? So okay, he got 9.3. So it may not be now a salt, because it is a salt, then your pH has to be, if it is only hydrolysis, your pH has to be less than 7, because it should be acidic. So it is now more than 7, it is not a hydrolysis, means it is not completely neutralized. So it was maybe a buffer situation. So you have some ammonia and some ammonium sulfate maybe, because the pH is 9.3. So what we see, if pH is 9.3, then for a buffer, that is like a basic buffer, which is a buffer of, here, that is NH3 plus NH4 twice buffer. So what is for the buffers is, POH should be equal to pKb plus log of the conjugate acid concentration, that is NH4 plus concentration by NH3 concentration, base concentration. So what is POH will be 14 minus that, it is 4.7. pKb is also 4.7 plus log of this ammonium ion concentration that we need to determine. From that we can calculate ammonium sulfate weight. So let us say we are calculating X or ammonium sulfate, then ammonia concentration is directly 0.2, because even you have 500 ml of this and you are adding a solid ammonium sulfate maybe to get that pH. So that this is 1, sorry, this is 0, that means it is log 1 on this side. So X by 0.2 is equal to 1, that means X is 0.2, means how many moles of the we have to add, or concentration of ammonium has to be, ammonium ion concentration has to be 0.2. So how many moles are this is there, means concentration is in terms of 500 ml. So if concentration is 0.2 molar, that is moles should be 1000 by 500, because we need grams of ammonium sulfate weight. So it is nothing but 2. So this is nothing but 0.1. So moles of NH4 plus is directly, I can say, 0.1. So what should be ammonium sulfate will be? Ammonium sulfate is giving 2 times of ammonium ion. So if you want 0.1 of this, I should take 0.05 of this, half of that. So what should be the weight? Moles are known already, because we are calculated moles directly. So moles of ammonium sulfate, so the weight of NH4 twice SO4 is 0.05 into molecular weight of that. So write molecular mass of that. That will give us the weight in terms of grams. Okay. So since the pH was not mentioned as 9.3, our idea is it's not a neutralized, ammonia is not completely neutralized, or even not neutralized, it is salt is not asked. He said ammonium sulfate should be added to ammonia. So it is directly buffer itself directly. Next, a volume of 250 ml of saturated solution of, or a clear solution of calcium oxalate requires 6 ml of 0.001 m KMnO4 in acidic medium for complete oxidation. So it's nothing but now a redox reaction that exists between them. So MnO4 minus reacting with calcium oxalate, or it only reacts or it only oxidizes oxalate ion, because calcium is spectator, because calcium is already in +2. It is the maximum possible oxidation state that it can possess. So it can't oxidize. In terms of acidic medium, so it converts into Mn+2, because permanganate oxidation state changes by 5 units, plus it converts into CO. So the N factor of this is 2, the N factor of this is 5. So how many moles of this was reacting? Is 2 moles of this reacts with 5 moles. So what we do is, we interchange the N factors. So now what is given for us? The 250 ml of a saturated solution we have taken, and our oxalate concentration exists to something, and it requires 6 ml of this 0.01 m KMnO4 in acidic medium. So we can use, let us say, the molarity relation directly like this, as M1V1 by N1 was equal to M2V2 by N2. Means we can determine what is the concentration of oxalate ion. So if you know the calcium oxalate ion concentration, calcium ion and oxalate ion concentration will be the same, because it is a clear saturated solution of it. So calcium oxalate is calcium +2 and C2O42. Means if it is S solubility, if it is a solid, this is also S. So the concentration of calcium and oxalate ion will be the same. So let us determine the calcium oxalate ion concentration, so that it will be calcium concentration also. Then Ksp is nothing but S square. So molarity of this was 10 to the power of -3. This one KMnO4. This is for KMnO4 we are using. This is for oxalate. Then the volume of that is required is 6. By number of moles that is consuming is 2. This is N factors, not number of moles. So then molarity concentration of that we are determining, oxalate ion concentration. Otherwise you can write this as concentration of oxalate here, or as we said S also. Then the volume that is consumed is 250. Then the number of moles of that is consuming is 5. So this is 5, 50. This is 3. Here. So this comes here in the denominator and becomes 50. So what is oxalate ion concentration, or S value is, it's a 10 to the power of -3 into 3 by 50. Means you can use this thing, that is, let us take 100 in this case. Means you are adding 10 to the power of -2 and 10 to the power of 2. So this I can write it as 100 into 3 into 10 to the power of -5 by 50. So it becomes 2. So it's 6. So 6 into 10 to the power of -5. That is S. So what is Ksp? Ksp is nothing but S square. That is 6 into 10 to the power of -5 whole square. So that comes out 36 into 10 to the power of -10. So but as given values are 36, 3.6. So this is our option. Okay. So we are determining the oxalate ion concentration. So because it is a saturated solution, the calcium ion also should be the same. So these are the basic like applications that we see in ionic equilibrium. This one. Let us see as the last thing now. The solubility of MNS in pure water, assuming there is a sulphide ion hydrolysis. So when the solubility of the components gets affected because of common ion effects, or common ion effect decreases its solubility, and it is also affected by the complex formations. So when the complexization is taking place, its solubility will increase, because completely it transforms into the complexes. So as you are getting the ion concentration, it tries to move into the complex formation. So as the reaction gives, a component gives that particular ion might be converting into complexes. So the reaction starts moving in forward direction during the solubility. So even there is a hydrolysis. the ion is sometime converting into the hydrolysis products. So what is, you see, sulphide ion hydrolysis? If you take sulphide ion, it's reacting with water, then it is maybe giving HS minus and OH during the first hydrolysis. What is Kw for this? Sorry, Kh for this? As Kw by where you are getting the sulphide ion is an important, because of this ionization of HS minus. What is this HS minus ionization? Is nothing but it's the second ionization of H2S, because he gave Ka1 and Ka2 of the H2S here. So it should be nothing but Ka2 of H2S. So it is 10 to the power minus 14. This is also 10 to the power minus 14. So this is 1. Means it's a little bit higher value when we just consider it. Maybe this HS minus also may undergo hydrolysis. That also we don't know, because he said sulphide ion hydrolysis only. But maybe there is a HS minus hydrolysis. Suppose HS minus hydrolysis will give H2S and OH minus. So when we consider the KH for this, that will be again Kw by Ka1 in this case, because where you are getting the HS minus is an important. That particular ion is coming from particular ionization. That K value comes in the denominator. So for a anion hydrolysis, what is the KH value? Kw by Ka. But what Ka we should consider it? We should consider the Ka which gives that particular ion. Similarly, base Kb. So which type of ionization of a base is giving that particular cation? So here it is nothing but 10 to the power minus 14 by given as 10 to the power of minus 7. So it is 10 to the power of minus 7. Means it is very low. So this hydrolysis will not be there. So this hydrolysis will be there. So what will happen? This is nearly, as we said, 1. So if you get, suppose, the MnS which is converting as Mn plus 2 and S2 minus. That means if S moles of this is dissolving, you will get S moles of this and S moles of this. So if S moles of this is coming here, since the equilibrium constant is 1 or higher value as we compare the second, so this will convert into S and S. So what is this? We consider it now. That is, the concentration of S2 minus also becomes now as the some X value, because it maintains. So this is your X. So what is your sulphide ion concentration? Sulphide ion concentration is nothing but here Ksp by Mn plus 2. Because you have to simplify the things. So Ksp value is now already there. Let us write later. Ksp by Mn plus 2, that is nothing but now S. But here what is sulphide ion concentration? This is nothing but now S square by sulphide ion concentration. Okay. So what is the sulphide ion concentration from here? The sulphide ion concentration from here is nothing but the S square. So if you just write Ksp, what is Ksp? Ksp is again nothing but Mn plus 2, Mn plus 2 Mn plus 2 concentration into the sulphide ion concentration. So this is nothing but S, this is nothing but S square. So nothing but it is S cube. But S cube is nothing but equal to now 2.5 into 10 to the power of minus 10. So already this 6.3, 0.63 whole cube is nothing but 0.25. Clear? So that was used. So from that approximation, maybe you can do it. Clear? So it comes out Now it's maybe you could just use it as 10 to the power of minus 12 here. This is nothing but 10 to the s cube. Means 10 to the power of minus 12 means you are making it as a 250. So you will get 0.63 whole cube is 0.25. So 6.3 you will get for the cube root of this. This is 10 to the power of minus 4. So your value comes out to be 6.3 into 10 to the power of minus 4. Clear? So this approximation as you do it, or you take the cube root of 2.5 into 10 to the power of minus 10, which comes out. Otherwise, you can take 0.25, 10 to the power of minus 9. I think here itself we can do like this also. This is nothing but, I think you can say, this is nothing but 0.25. So 0.25 into 10 to the power of minus 9 is nothing but s cube. 0.25 is nothing but 0.63. 0.63 into 10 to the power minus 3. So we are writing 6.3. Clear? So this is how we can see, let's say, the time. So we could able to cover the solubilities, pH related things, hydrolysis related things. Clear? So the buffer related things. So to the extent what we can cover, we covered. So just practice, then we will